Okay, by the way, we could sit down and draw the circuit diagrams for all possible combinations. That would include all the different possible inputs and all the different possible outputs. Well, really, it's based on the outputs, and since there's 4 possible outputs, that means there are 2 to the 4th possible combinations of outputs that are possible, aka 16. So here's the truth table for 1 through 8, and then 9 through 16. And that would be all the possible inputs, output combinations for our 2 input, 1 output circuits. We're not going to do these. And I'll tell you right now, in general, you just need those. We're not done yet.
I'm just putting my thing.
I'm just telling you. Those are going to be your building blocks over there, not NAND, AND, OR, and XOR. The next other one that you can use called NOR, negated OR. You OR 2 things and then you negate it afterwards. You want to take a guess of how long that's going to take? I mean, you have an OR and we have a NOT. Just put them next to each other. Now it's going to take 3. All right. Okay. So from that level of abstraction, a processor is simply a bunch of these gates over there. And by the way, there's a proven theorem that all gates can be built from either NANDs or NORs. So they're really just a bunch of NANDs or a bunch of NORs with some wires connected to them, and that's all your processor is. Another level of abstraction or a different way to look at a processor. All right, now we're going to stop here because we're programmers. We're not electrical engineers. This whole drawing thing and chalkboard, it's a little tedious. We should have a tool for it, and we do. So, did someone say yay?
Yeah.
Yes, we do. Yeah, we do have a tool for this to automate this, so we don't have to constantly draw everything. Now, it's not going to draw the circuit diagram for you, but you can program in your diagram and you can run simulations and actually see what the output is. So this is an incredibly handy tool, and this tool, well, we're going to study Verilog. The 2 big ones are Verilog or VHDL. Both of these are used by industry. I can tell you right now, Intel, AMD, Sun, well actually Oracle now, all of them use either Verilog or VHDL in order to create their processors. So this is a language that's used. We're going to be using Verilog. I choose Verilog because it's simpler. It's also what I studied and what I've used. VHDL is more verbose in certain, but depending on the situation, one is slightly better than the other. But for this class, it doesn't matter. Well, Verilog's simpler, so we're going to stick with that. You, of course, can go look this up if you want. So when you're coming up to solve your problem, aka understand the problem, identify the inputs and the outputs, draw a truth table, is going to be very helpful. Step 2 is simplify your logic. We have not talked about this, but there are ways to optimize your circuit because the circuit you probably come up with initially is definitely not an optimal circuit. There are techniques in order to improve the performance, aka reduce your gate delay, as well as reduce the number of gates that you have to put on your processor. By the way, those are both costs, because the more gates you have on your processor, the more power it's going to consume. And of course, the higher gate delay is, the longer it's going to take. And yes, it is unfortunately a trade-off. There are many situations where you can have a very few gates, but then it takes a very long time. Or you can have a massive number of gates consuming a ton of power, but your gate delay is very low. And we will get to that. But we're not going to talk about automating that right now because we want to talk about the tool. And then you implement your design with logic gates and then use Verilog. Okay. Ways to specify a circuit, we could draw schematics, which is what we've been doing so far with our gates. But we can also try and describe them with some type of an HDL. It is not a programming language per se, it is a description language. You are describing what needs to happen. You're not describing how it happens, you're describing what needs to occur. And then Verilog is going to run the simulation. This is very important to get the difference because if you try and think of it as a programming language, executing one step at a time, you're going to run into trouble and probably never get a hold of Verilog. But it's Verilog's job in order to produce the simulator for your design. All right, Verilog, VHDL, they're both IEEE. Verilog's simpler, VHDL is more structured. We're going with Verilog. It is a simulation tool. It models what a circuit does. You say multiply a star, and then it's going to simulate how it implements multiply in circuits. There are actually ways to change how multiply works, but we're going to implement multiply ourselves at some point, not right now, we're not to that stage, but we will. It allows you to test and allows you to execute a design to verify correctness, which is probably the most important aspect of Verilog. Synthesis is going to convert your circuit diagram that you instrument inside of Verilog and change it into a net list. You take that net list and you send it over to your layout. The people in layout figure out where all the nets and gates go. On a PCB, they create a kind of an EDA file. They send that over to their manufacturer and stamp, create a processor for you. This is a whole process, but it doesn't really matter for you. Just know that you're doing your HDL description, which has a simulator, and you can do functional validation. These are all the other steps that need to happen to get a real chip, but we're not going to worry about that. We're only worrying about describe it and do synthesis. The EE people, they're on this side. But we're architects, so we're over there. All right, we're going to skip this. So how do you specify a circuit? There are three main ways to do it. We're going to stick with the structural method here. I wish I had a nice big pointer. So let me read this diagram for you out real quick. There are three inputs in this diagram, A, B, C. There are two outputs, X and Y. All right. C first goes to a NOT and then is piped directly to Y, and then is also piped to the input of gate 3. And we're going to call gate 2 a NOT, or G2. G1, gate 1 takes the two inputs of A and B, produces an output. We'll call that wire E, because we have to label what this wire is, and then we'll pipe that over to G3. So in the structural model, we describe that there's a wire. We create an AND gate, pound 2, that's the gate delay. Hey, look, just like that up there. So pound 2 or hashtag 2. It's on the gate delays, calling it gate 1. So this AND is going to be called gate 1. The output is E, right there. And the two inputs are A and B, which are those two wires. Next, we're going to describe this NOT. One gate delay, boom. Call it gate 2. The output is Y, the input is C. Why do we call it Y? Well, it goes directly to the output Y. Next, OR, let me use my mouse pointer for the online student. OR, 2 gate delay, calling it gate 3. There's G3. Inputs are output's X, input is E, which was the input from this gate, and the other input is Y, which is the output of that NOT, and the final output's X. So you describe it like this, and then Verilog can run the full simulation. By the way, what's the total gate delay of this circuit? What is the longest path?
Through the OR.
Right, so we got to go through the AND, which costs 2, and the OR, which costs 2, so the total gate delay is 4. This NOT happens in parallel to the AND, so that NOT finishes saturating even before the AND finishes saturating. So the NOT happens in parallel. Okay. The structural way of writing it is how you're going to write it for your assignments. Okay? There are 2 other ways to do it. You can do behavioral, where you assign E equal to A and B, similar to the syntax you're used to C, and do assignments that way. The other way is something called behavioral with the always block, and we'll get more to that next class because we're running out of time. But this is a little bit how Verilog looks. Next class we'll go in and we'll start doing actual examples of Verilog, and we'll start getting used to it. Hopefully everyone will have the iVerilog compiler implemented or installed. Okay, lastly, before I forget,